Hello, today we are playing Space Engine. So the first thing here is that we're on a planet in the Andromeda Galaxy. One disclaimer here is that some of the things in this video are not real and were procedurally generated by Space Engine. So first, we're going to go to the place, the closest star to Earth in the Milky Way. Proxima Centauri. The Proxima Centauri is a red dwarf type star, and it's the closest star to the sun, and it's only about 5 light years away. But if I'm going to try to look for a sun here. Let's try to look for a sun. Okay, there. There, that's our sun. That is our sun. From Proxima Centauri, our sun would appear like it's in the constellation. Our sun would appear like it's in the constellation Cassiopeia. Since that is the closest star to Earth. Since that is the closest star to Earth, it might look. Some constellations might look a little weird, such as, let's say, Centaurus, where only Alpha Centauri is all the way here in the Scorpius area, but it's actually in Taurus. That's because Alpha Centauri would be only 0.2 light years away from Proxima Centauri. These two are the closest stars to our planet. So if we turn off constellations, we can Proxima Centauri does have planets. Let's start with Proxima Centauri D. Even though Proxima Centauri D is very, very far, even though Proxima Centauri is very close to Proxima Centauri, the star, it might look like it's actually negative 56 degrees Fahrenheit, and 1 year on this planet is only 5.1 days. And another thing is that a year and a day on this planet is the same thing, the exact same thing. So whenever a year passes by, a day also passes by. It takes the exact same time for a day to pass on this planet as rotating around the star. And the reason this happens is because of something called tidal locking. Tidal locking means this planet actually doesn't rotate at all. How this happens is when this planet doesn't rotate at all, the only thing it does is revolve. It doesn't rotate. So one side at the day, one side will be scorching hot, and the other side will be negative in the 200s. It's impossible to live here, but it's most of the time Proxima Centauri D is very rugged, has a very rugged surface, and is very arid. If I land here, it might take some time. Okay, anyway, let's go back up. So this place is has mountainous terrain, but for Proxima Centauri D, based in Earth, this won't be called mountainous terrain. And also most of the planets in the Proxima Centauri D system have aurorae. If you've ever went up to the north, it's like places like Scandinavia, then auroras happen a lot there. Like these. and the next planet is Proxima Centauri b. So this is not how it looks like in real life. In reality, it has the ability to support water. But it also, in reality, it could have life and also has the ability to support water. Its atmosphere so it's the closest planet to Earth, but it could also be it's also possible for this planet to have life on it. It might not look like it in this, but it could. It has the possibility to. So let's go into the wiki for this climate. In this climate, it looks like it has a very, very bad climate temperature. So based on this, it actually keeps us real time on the temperature right now. It's not actually real time, but if the simulations of right now existed in there right now, then this is what the temperature would be. So then let's go to the last planet, Proxima Centauri c. This planet is the farthest planet from the star. It also, as you can see, it also has some very thin rings. As you can, it also has some very thin rings. And it's a case like Proxima Centauri d, like it's impossible to live in because of no water and it's very arid, but all of this planet is like Antarctica. Is like an Antarctica because the average temperature is about 230 degrees Celsius. So if we go to here, Proxima Centauri c orbits at 1.4 astronomical units above the star Proxima Centauri. 1.4. Our Earth orbits at exactly 1 astronomical unit away. Exactly 1. Proxima Centauri b orbits at exactly this much. Wait. Proxima Centauri b orbits at less than an astronomical unit away. I can't tell if it's astronomical unit, but an astronomical unit is 91 to 93 billion 93 million miles. So in kilometers, it should be about 106, 100 in the 100s. So it's less than astronomical unit. And for Proxima Centauri d, it's even less, about half of Proxima Centauri b. So if we go to Proxima Centauri, if we turn on the orbits and then go out like this is the orbits. The Proxima Centauri d orbits here. Proxima Centauri d orbits here. Proxima Centauri b orbits here. What astronomical unit should be about here? What astronomical unit actually is a lot farther out. Like, let's say Proxima Centauri c is also extremely far from Proxima Centauri d and b's orbits. Proxima Centauri d is there, Proxima Centauri d is there, Proxima Centauri b is there, and Proxima Centauri c is this. And even that, an astronomical unit. An astronomical unit. An astronomical unit actually should be about, if we line ourselves up here, astronomical unit should be about this distance, like right there. And if we zoom out, like right here, the orbit around here is an astronomical unit. If this is an astronomical unit, this is Proxima Centauri C. Our Earth should orbit around here. But that means our planet just the same size as Earth, and it's actually colder than Earth, orbits all the way in here. So if we go to the solar system, let's go to Earth. If we go to Earth here, if we zoom out, this is the Earth's orbit, the one that's highlighted, this one. So, but then Proxima Centauri C should orbit somewhere in the asteroid belt, somewhere here. Yeah, but that means Proxima Centauri B and D should orbit somewhere here, around here, around maybe here. And to give you the scale of that, it's around it's right there. This is the Earth. Should be Proxima Centauri. And also, speaking of the asteroid belt, this is how many objects are scattered around the solar system. A lot. And there are even these objects in the Oort cloud. Look at all these objects. We also have the moons of Jupiter. We also have a lot of Jupiter moons and Saturn moons. But still, this is how many objects exist in the entire solar system, and there are still that many more. So now going to the next peculiar object we have is Luhman 16. Even though it says it's a star, there's something very, very intricate about this system. This is Luhman 16A, and this is Luhman 16B. These don't look like a star. At least this one's not a star. But this one is actually classified as a star. It's called a brown dwarf. A brown dwarf is basically a failed star. Like a planet, sometimes a planet goes in the same type of evolutionary path covered in the evolutionary path was covered in the earlier video. That path was from if a planet didn't go in this path. If a planet did go in the normal planet path, it would become a star. It could become a star. And also, let's take a moment to think about. We can still see our solar system's comets from here. We can still see our solar system comets, the blue things we see there. We can still see the comets. So if we turn those off, this is Luhman 16A. It's a brown dwarf. Luhman 16A is a brown dwarf. It's a failed star. It's like Jupiter. It's like Jupiter, but extremely hot. It's like Jupiter, but extremely hot. So let's get to info. In the general info, the size of the apparent size. Oh, the size of this is about 0.06 sizes of the sun. It's about 0.06, and its mass is 33.5 times the mass of Jupiter. It's actually closer to the mass of Jupiter, but it's still classified as a star. The temperature of this is 1,250 Kelvin, and our sun is about 5,000, is in the 5,000 and 6,000s for Kelvin. Let's make sure. Let's make sure it's in that. Sun. Okay. Our sun is 5,778 Kelvin. But Luhman 16A is 1,350. But still, it's still classified as a star. Even though this is very cold for a star, you would hear people calling this a cool star, like a cool star, But still, even though it's called a cold star, it's still extremely hot based on everyday item. Because if you were to go with this, it would be about as hot as lava. Then if we go to Lemon 16B, we can see that this is also a brown dwarf. This is also a brown dwarf. So we'll be covering brown dwarfs in another video, but we'll cover the spectral types today. A spectral type of a brown dwarf. The spectral type of a brown dwarf Earth comes in three characteristics. The L-type brown dwarfs, like Lemon 16A, are usually the brightest and are usually when you think of brown dwarf, this is what will usually come to mind. A darker, dimmer red dwarf. And sometimes it has gas worlds just like Jupiter. And there are also T-type brown dwarfs, like Lemon 16B. They're a lot darker and cooler than L8V type stars. This one has a temperature of 1,210 Kelvin. They're a lot cooler, but they're still classified brown dwarfs since they also emit light. The next word we're going to go is wise. I keep forgetting the name. Let me go do something. I'm going to search the name up. List of objects. List of stars from to list of near stars and brown dwarfs. Okay, the name of it is Wise. I know the name is Wise, but it's Wise 0855. Wise 0855 dash 0714 dash 0714. There. So if we so let's go to wait. Wise 0855. Wise. There. I think that's it. 5055. Why? Okay, there. So if we go there, this might not look like a brown dwarf to you. And where did I go? Oh, I'm just somehow inside the brown dwarf. Where am I? Oh, I don't know what happened. First, 1 second. So, this is the only reason this is dark right now. It should look like a brown dwarf when we light it up. But at this moment, if we turn on HDR, even if we turn on HDR, it's just doing this. So In reality, this is actually what this looks like. No, this is just this is a Y-type brown dwarfs. They're also called called rogue planets and planemos. Since most Y-type brown since most Y-type brown dwarfs aren't made from the from the planet doing the star process instead of the normal planet process. It actually is from a planet it's actually from a planet that is doing that was kicked out of his star system. So this is only 350 Kelvin. And also this if we can see based on this it okay, so here okay, so we might be able to see there. That's what it should look like. In the top corner, in the top left corner, you can see this, and that's what it should look like. But it doesn't, because of the fact that there's no light around here. Lemon 16. Okay, now let's go to lemon 16 again. I'm going to show you something in lemon 16 galaxy. This is a binary planet. It's called a binary planet because there is something called a barycenter. This is an orbit around lemon 16. In this orbit, it's like this. It has two planets that are going in the same center, and they sometimes intersect orbits. The only reason this happens is because of oh, sorry. My computer failed to load the brown dwarf again. My computer failed to load the brown dwarf again. My computer failed to load the brown dwarf. So this is what the brown dwarf should look like. But with HDR, we can see that this brown dwarf is actually has light emanating from it. If we go here, we can see that it does have light emanating from it. Let's go. Okay, so light does emanate from this black hole. Not a black hole. Brown dwarf. Like light comes from this black hole, but in normal mode, since all the stars are obstructing the light of this, it will look like this. So let's move on to the next star system. So my next star system might be serious for you, but the reason is because my computer crashes when I go near a degenerate star. If you don't know what a degenerate star is, I'll talk about it here. A degenerate star is a black hole, a pulsar, or a white dwarf. The closest white dwarf to us is Sirius B or Procyon B. But the problem, a white dwarf is a stellar remnant. A black hole happens when a massive star explodes in a supernova. But a neutron star or pulsar is what happens when a smaller star erupts in a supernova, but it could also be a pulsar if it rotates rapidly at more than 100 times a second. And then Sirius and then a white dwarf is the stellar remnant of star that is less massive to even create a stellar remnant other than a white dwarf. So if it's not massive enough for it to collapse in on itself, or also just explode, if it's too massive for it to just collapse it on itself, or just do this, or just or become a stellar degenerate that spins fast, it becomes a white dwarf, which is basically a core of a normal star. But the thing is, my computer crashes when I go near these because a lot has to happen at once for it to actually load one. So we're going to keep skipping. We're going to skip that. And go to the next place we're going to go. So the next place we're going to go is somewhere you might have not heard of. It's called Regulus. Regulus. It's 80 light years away from a normal star. This Regulus Regulus is in the constellation of Leo. It can be called Regulus. You can also call it the Lion's Heart, Cor Leonis, Basilicus, or just Alpha Leonis. It's a Regulus is a Regulus is a binary star. Regulus AB. Regulus is actually a quadruple star. Let's AB has a white dwarf in it, so I'm not going to go there. So A Leonis CD. C and D is an orange dwarf. D is a red dwarf. D is a red dwarf, and that's F. And C is an orange dwarf. There are no planets in this system. There's no planets in the system. It's just normal. It's just a normal system. So the next place we're going to go. Wait. Deneb. Wait, I want to see if the star has. No, this star doesn't have any Denebola. Denebola. Okay, this star has. This is Denebola. I'm gonna go to Denebola. Denebola. This is a real star. This is a real star. It has some of the planets aren't that real though. Aren't real. But still, for the sake of it, we're going to explore most of them. Well, but actually, let's just do this one since. Look at this planet. It's filled with oceans and it has rings, and it has these cool fading rings And then let's go and click this. It has these fading rings. But still, places. Let's go to Denebola 7. This is a cold ice supergiant. It's like Uranus or Neptune, but it's really just a normal planet. So let's see the moons of this. But okay, most of the moons are just moons like these. Wait. So this is the largest of all its moons. It does have an atmosphere. Its atmosphere is made of krypton. This planet's similar to Pluto. It's not a planet. It's actually a moon, but it's similar to Pluto since its atmosphere has that bluish haze. But the only problem is the atmosphere composition, which is mostly krypton. Krypton, even though krypton sounds weird as a atmospheric compound, it can happen. As you can see, it has a heavily cratered surface. So, next place, Rigel. Let's see if wait. I think this place has a degenerate star. Okay, there's no degenerate stars. It's just a there's just no planets for us to explore, but we're still gonna go there. Rigel. Right. Rigel is a 3-star system. This is Rigel A, the Rigel we all know about. Rigel B. Rigel B, the other Rigel B, and Rigel C. Rigel is a normal. Rigel is Orionis is Beta Orionis. Beta Orionis. That means it's the second most brightest and massive star in the constellation Orion. After, you probably know where this is leading. You probably know where this is leading. Betelgeuse. Betelgeuse is a supermassive star. It's more like a hypergiant than a supergiant. It's extremely large, and this is Alpha Orionis. In fact, the sheer size of this is the sheer size. Let's actually see the size of this. Let's see the size. If we go to Wiki. Okay, so if we go to info, we can go to general, and we can see its size at about 0.05 light years. And in reality, and that's actually smaller than you might think. It's only at least 1 or 2 astronomical units wide. In reality, we don't know if Betelgeuse does planets yet, but still, again, bear with me for a second. This could be Betelgeuse 1, Betelgeuse A. It's got a torrid air on Earth for a reason. It's orbiting 2.1 astronomical units away, and when you see it, it might not look like this, but when you look to the other side, you'll quickly realize why it's extremely hot. A sunrise on this planet would just look horrendous. It's only about, from Betelgeuse, it's only about a few hundred kilometers, a few thousand kilometers away. And its atmosphere is made. Nobody would want to live here. That's all. Nobody would want to live here. Let's go to this. This is even closer to Betelgeuse. It's an asteroid, but it's an asteroid. And also, this is a time where terrain generation starts to glitch out in Space Engine, where the front part seems to be a lot hotter than the back part, and it has a designated line between them. So my computer fixed that. My computer just fixed that. But still, sometimes terrain generation bugs out like this top part. Which clearly shouldn't be very cold compared to the rest of the asteroid. So let's go to the next planet. Torrid gas giant, torrid arid summer, hot ice giant, hot arid. So let's go to this planet. Even though it might look like it could support life, it's still very, very close to the star based on the sun. It's still 500 degrees Celsius, but it's one of the colder planets in this whole system. And most of the atmospheres in this system remain similar, but let's go down here. So the next place is this Betelgeuse C, I guess. It's close enough to the star that it still has these heat marks on it from being very close to the star. It's that close to the star, but still, it does have like this. But it doesn't have it isn't overwhelmed with heat marks like this one we found earlier. Let's go to the next star. when we go here in the next video, I'll have to think a lot about which star we have to go to next, because some of these stars will get very boring after some time. Oh wait, I just got an idea. Alpha Andromedae, Alpheratz. Let's see how far this star is. Oh, okay, that's close enough. That's close enough. That's close enough. There. This is Alpheratz. It's called Alpha Andromedae. It's another binary star system, but it's the only reason it's called Alpha Andromedae is because it's in the same constellation the Andromeda Galaxy is in. Not literally, but from Earth. From Earth, it looks like the Andromeda Galaxy within the constellation Andromedae, which is where the galaxy got its name, the Andromeda Galaxy. So let's go to the Alpheratz. It's a double star system. Alpheratz A is known as Syrah. Alpheratz B is just known as Alpheratz. Alpheratz A can be known as Syrah, and Alpheratz B can just be known as Alpheratz. And there's no planets in the system. It's just a normal system. The next one is closer to our sun than you might think. Teegarden star. Teegarden star. Let's see. So if we go to Teegarden star, it's close to our sun. It's very close to our sun. This is the Teegarden star. It's very, very close to our sun. It's one of the main places people might think of. It's one of the main places astronomers might think of for life, other than Proxima Centauri. So let's go to Teegarden star B. It's the main place people would think. And unlike Proxima Centauri, its base engine it actually renders as an oceanic planet. It's just a little bit too oceanic, since it says it's a super oceanic aquaria. And if you don't know about Space Engine's naming system, super oceanic means that it has oceans that are hundreds of kilometers deep, deeper than the Mariana Trench. Teegarden star C is a cold air aquaria. It's like a desert. As you can see, it's just the same system. It's the same kind of Proxima Centauri C. It's a cold air aquaria. It's like Antarctica the whole way through. It's just an Antarctica for an entire country, for an entire planet. Teegarden star D. This planet is known for having. This planet has also in the same case as Teegarden star C and Proxima Centauri C. It's also one of these stars with a cold one, and also Teegarden star D was only discovered this year in 2024. So it's one of the newer planets to be discovered. And then let's go into Proxima Centauri, because Proxima Centauri C was also Proxima Centauri D was also only recently discovered in 2020. Proxima Centauri B was discovered since 2016, and Proxima Centauri C was from 2019. Proxima Centauri was known since who even knows. But it was known since who even knows, because we don't know if ancient cultures had telescopes already and just were just lost to time. But next, Proxima Centauri C. After Proxima Centauri C, we're going to go to the last place we're going to for this video, because it's getting very late. So TRAPPIST 1. It's only about 44 light years away from Earth, and it's probably the best candidate for habitation yet. In the first case, start with TRAPPIST-1b. It's a warm, airless Earth. It's like Mercury. It's the TRAPPIST-1 alternative of Mercury. It's just larger, since it's actually larger. It's about the same size as the Earth, but its atmosphere and things like that are practically the same as Mercury. It's tidally locked. TRAPPIST-1c. This is practically also the same as Mercury. This is also a Mercury-Venus combo, but it has many ridges on its surface, as you can see right here. It has ridges and just small craters. TRAPPIST-1d is where things get interesting, because TRAPPIST-1d. If we remove the clouds. If we turn off clouds, we can clearly see that TRAPPIST-1d, it has water. And but the problem is the waters are made from liquid carbon dioxide, and the average temperature is only about negative 114 degrees. Then TRAPPIST-1e, TRAPPIST-1f. Oh, so space engine. Once again, Space Engine doesn't really have good catalogs for these planets. It's okay. I'll explain in another video. But in these catalogs, a cooled arid aquaria. This is a cool arid aquaria in Space Engine, but in real life, it's probably going to be more habitable than Earth. In reality, TRAPPIST-1f, E, and D will all be in the habitable zone for this star. And they will all have at least an ocean on its surface. TRAPPIST-1g and TRAPPIST-1h are just like the Proxima C and Teegarden star C. Teegarden star D. It's just Antarctica. It's just Antarctica if it was a country. If it was an entire planet, I'm going to say. So that sums it up for this video. In the next video in the series, we will talk about other stars more than 200 light years away from this whole solar system. So enjoy, and I hope you all have a good time. Bye.